Hello guys, welcome back. Today we have got another video in the series of anti-infectives, that is antifungal agents. Already in the chapter of anti-infective agents, we have finished local anti-infectives, preservatives. Now the next topic we are going to talk about is antifungal agents. So let's get started. Okay, so starting off simple, what is a fungi? So a fungi is a eukaryotic, sporophytic and parasitic microorganism that can be unicellular or multicellular and having chitin in the cell walls and ergosterol in the cell membrane. Now let us break it down for you. Eukaryotic. What do you mean by eukaryotic? Eukaryotic is the new kind of cells. Prokaryotes are bacteria and all such cells. Fungi is a eukaryotic cell. So they are sporophytic and parasitic. What is sporophytic? Sporophytic as in they produce spores. And parasitic as in they depend on others for their nutrition. Now they can be either unicellular or multicellular. Unicellular, the example of a unicellular fungi would be yeast, and multicellular is a mold. They have chitin in their cell walls and ergosterol in the cell membrane. If you look at this picture over here, the yellow color, this layer right here, is chitin, and the pink one in the inside, this one, this is the ergosterol. So chitin in the cell wall, and in the cell membrane we have ergosterol. Now, fungi is divided into two types, yeast and molds. As I have told you the difference, yeast is unicellular, whereas mold is multicellular. Yeast will propagate by budding and mold will propagate through hyphae production. Now some examples of yeast would be Blastomyces, Histoplasma, Candida, Cryptococci. You all might have heard about Candida albicans, which will cause candidiasis. So that is a member of the yeast family. And molds, we have Aspergillus, Dermatophytes, and Mucor. So you all might have heard about the black fungus. So the black fungus was caused by mucor. That is, the black fungus disease was known as mucormycosis, caused by Rhizopus species. Next we have what are fungal infections. So fungal infection is a disease caused by agents like yeast and mold, which affects the skin and other internal organs. Now based on the location of the infection, we have two types of fungal infections. We have superficial mycosis and deep-seated mycosis. In superficial mycosis, like only the outer areas of the skin or maybe the scalp or the nails will be affected, whereas comparatively deep-seated mycosis will be a systemic infection. That is, it can go inside your blood, bones, and all the other internal organs. So, superficial mycosis, that is also known as dermatophytosis. So, it is a contagious skin infection limited to the epidermis layer. It can also cause lesions in the skin, nails, and hair. It is caused by dermatophytes, which will digest the keratin in the hair. Now, systemic mycosis is it will happen in the internal organs. It can affect the CNS and it is mostly non-contagious. Now let us talk about antifungal agents. So antifungal agents are the medications or drugs used to treat fungal infections which are caused by various types of fungi. Now some examples would be ketoconazole and amphotericin B. Now as we know, ketoconazole, it is a very common ingredient in shampoos, that is anti-dandruff shampoos. And amphotericin B, it was used for black fungus, so amphotericin B. So in the classification of antifungals, we have first off we have azoles. Now azoles are nitrogen containing compounds. Azole, so a nitrogen contained in a compound. So in azoles we have two subtypes. First we have imidazoles, the second is triazoles. Now imidazoles are two nitrogen containing compounds, whereas triazoles are three nitrogen containing compounds. Imidazoles will include miconazole, ketoconazole, butaconazole, and oxyconazole, whereas triazoles will contain fluconazole, itraconazole, voriconazole, terconazole, posaconazole. Now the most commonly used nowadays is posaconazole, and in here ketoconazole. Now among the imidazoles, all of them except ketoconazole, that is miconazole, butaconazole, oxyconazole, these are non-systemic, whereas only ketoconazole is systemic. Next we have triazoles, that is fluconazole, itraconazole, voriconazole, turconazole, posaconazole. These are all systemic drugs. Now, how do we remember this thing? So, okay, so we can remember like MC book. So, M for miconazole, C there is another one known as clotrimazole, B would be butaconazole, K would be ketoconazole, and one more oxyconazole. In triazoles, we have fluconazole, itraconazole, voriconazole, turconazole, posaconazole. How will we remember this? We will remember with the acronym of FLIRT. FLIRT. Now, if we rotate L a little bit, we will get a V. So, FVIRT. So, F for fluconazole, V for voriconazole, IR for itraconazole, and T for turconazole, and an extra posaconazole. So now we have completed azoles. Next we move on to antimetabolites. In antimetabolites we have flucytosine. In alkylamines or in allylamines we have terbinafine and butanafine. In antibiotics we have polyenes, heterocyclic benzofuran, echinocannabinoids. Polyenes means there are multiple double bonds or unsaturated bonds present in the compound. For example, we have amphotericin B, nystatin, and hemicin. In heterocyclic benzofuran, heterocycle. So a heterocyclic compound is one compound which has different kinds of chemical moieties in its ring structure. Now, since there is benzofuran, there is a condensed structure of benzene and furan. So the example for such a compound would be Griseofulvin. Next we have echinocannabinoids. In echinocannabinoids we have examples like Caspofungin, Micafungin, and Idolafungin. So we can remember echinocannabinoids as like Eskimo, Canada, and caps of mica. Now, as we know, Eskimo is a place which is made up, it's like a house which is made up of snow. So, snow is found in Canada. So, Eskimo and Canada. So, echinocannabinoids and caps of mica. Caps of mica. Mica is a white color element. So if we powder mica, it will look like snow. So caps of mica. If you see the mountains, there would be like a cap of mica. So Caspofungin and Micafungin. Next we have other topical agents. In other topical agents, we will have benzoic acid, undecylenic acid, and Tolnaftate. So one more thing to remember, Allylamines is terbinafine. Turbines, remember turbines, and butanafine, we can remember beauty. So turbines and beauty. So turbinafine, butanafine. That was the classification on the basis of the chemical structure. Now if the classification is based on the source, that is now it's natural or synthetic, we will have this. Now the gray color caps which you can see over here, these will indicate the synthetic compounds. So azoles, antimetabolites, and in allylamines, terbinafine. All these are synthetic along with tolnaftate among the other topical agents, and all the natural ones include butanafine. Then in polyenes we have amphotericin B, nystatin, hemicin. Heterocyclic benzofuran we have griseofulvin. Echinocannabinoids we have caspofungin, micafungin, and idolafungin. And in other topical agents we have benzoic acid and undecylenic acid. Let us see the general mechanism of action of these antifungals. We'll start with allylamines. So what do allylamine drugs do? There is the basic structure of the cell wall is made up of ergosterol. So for the production of ergosterol, acetylcholine is converted to squalene, which is further converted to lanosterol, and then lanosterol is converted to ergosterol. So what allylamine drugs will do is they will inhibit the conversion of squalene to lanosterol. The azoles will inhibit the process of conversion of lanosterol to ergosterol. So there would be inhibition in the cell wall production, and if there is inhibition in the cell wall production, the cell wall will become leaky, and due to the loss of integrity of the cell wall, there would be leakage of all the cell contents, which will eventually lead to the death of the fungi. Next we have flucytosine, which is an antimetabolite. What will happen is, after it permeates into the cell or it enters the cytoplasm, it will be converted to 5-fluorouracil. Now 5-fluorouracil will go and interact with the fungal RNA. Since there is disruption in the fungal RNA, it will inhibit the protein synthesis. Next we have the polyene antibiotics. The polyene antibiotics will bind to the ergosterol and they will increase the membrane permeability. So it will allow the influx of certain ions or molecules which will lead to the death of the fungi. Next we have imidazoles. Now in imidazoles we will learn 4 imidazoles, that is miconazole, clotrimazole, butaconazole and ketoconazole. Now in miconazole, this is the structure of miconazole. It may look a little difficult, but we will learn it partwise. So the basic structure for miconazole would be, since it is an imidazole, we have a 2 nitrogen containing moiety. So 2 nitrogens, 1 nitrogen in a 5 carbon in a 5 membered ring. So since this is a imidazole, so we have kept the imidazole ring ready. Now miconazole, so we will have a ring with 2 chlorines attached to it, 1 and 2, and next to 1 chlorine we will have a CH2 group attached. Now all we have to do is join this ring. So we will keep an oxygen in the middle. Now to this we will add an oxygen. To this oxygen we will just draw a mirror image of this part. So another CH2 here, attached to this another benzene ring with a chlorine here and a chlorine here, and next to this we will attach another CH2 which will be connected to a imidazole ring. Now this will be our micoconazole. Next we have clotrimazole. Clotrimazole is very easy. ClO means chlorine, then tri means something, 3 molecules. Imazole means imidazole ring. So what we do is we draw 3 benzene rings, 1, 2, 3, and an imidazole ring. Nitrogen, nitrogen. So we will attach all these 3 to 1 carbon, and the one closest to the imidazole ring we will give it a chlorine. So this is your clotrimazole. Next we have ketoconazole. So for ketoconazole, this structure would be very similar to a miconazole, that is a benzene with 2 chlorines, an imidazole connected to a CH2 group, that one attached to another C which is attached to oxygen, and then we will have this as the extra group. So since the name states keto, keto means a ketone group, so CH2 C double bond O, CH3 sorry, C double bond O, and then we will have a 6 membered ring with 2 nitrogens. Then we will have a benzene ring followed by an oxygen, another CH2 group, then attached to this would be a 5 membered ring with 2 oxygens, 1, 2. Now we will attach this carbon would be attached to a benzene ring with 2 chlorines, and here this carbon will be attached to another carbon which will be attached to a imidazole ring. So this will give you your ketoconazole. Now when it comes to oxyconazole, so we have this as the common one, a benzene ring attached to it will have two substituents, that is two chlorines and one CH2 attached to an oxygen. Same way, another benzene ring with two chlorines attached to a carbon. This one common, and then an imidazole ring attached to a CH2. This also would be common. What is extra here is a nitrogen group which attaches all three. So we will have a benzene ring. Attached to it we'll have two chlorines, common of us. Then we'll have CH2, oxygen. Now, attached to this oxygen we will have a nitrogen which is attached to another carbon, which will give rise to two things. One is a benzene ring with two chlorines, and next we have another carbon attached to a 5-membered imidazole ring. Now this is your oxyconazole. The only thing is this will be one part. We knew this needs a CH2, so this is another part. Another carbon attached to another carbon with this. So this two will be fused along with the extra nitrogen over here. So this is oxyconazole. Next we have fluconazole. In fluconazole we will have the same basic structure of a benzene with two chlorines, but instead of chlorine here, since it is a fluconazole, we will add a fluorine group. Now this is the easiest one. What we will do is, we will take a benzene ring, we'll attach two fluorines, to the next one we'll attach a carbon group, to that carbon we will attach two CH2 groups and then give them the triazole, that is nitrogen. In a 5-membered ring we have three nitrogens, so one alternate and one very close to this nitrogen. So one alternate to this nitrogen, one just adjacent to this nitrogen. So in here we will give the double bond over here, the other one here, this one, and then another triazole right here. As we said, one alternate, one just besides the nitrogen. So this is done, and an extra part would be giving an OH right here. So this is a fluconazole. In itraconazole, this is very similar to a ketoconazole, but the only difference here is, in this, instead of a ketone we have this compound over here. So we have a triazole with a ketone group. So we have a carbon attached to 1, 2, 3. So 3 carbons attached to 1 carbon, we have a CH3. Then we have a five-membered ring, nitrogen alternating, nitrogen just adjacent to it, a ketone group in the middle, double bond right here. Next we have a benzene ring. After the benzene ring we have a 6-membered ring with 2 nitrogens on the tip, then another benzene ring attached to an O, CH2, then we will have a 5-membered ring. So oxygen here, this carbon attached to a benzene ring, a chlorine here, a chlorine here. Attached to this carbon we will have another carbon attached to a triazole ring. So nitrogen, one alternating, one right next to it, double bond. Now how do you remember ketoconazole and itraconazole? In ketoconazole, first we had a ketone group followed by a 2 nitrogen tip group, then a benzene group, and then we had an oxygen, and then followed by the normal thing. In itraconazole we will have a 3 carbon group with a CH3 on the last carbon. Then we have a nitrogen attached with a double bond O, another nitrogen, another nitrogen. So this is also a triazole ring with a ketone group. Then we have a benzene, then a 6-membered ring with 2 nitrogens, another benzene ring, an oxygen, CH3, then a 5-membered ring with 2 oxygens. In the tip we have one leading to CH2, this is the triazole ring, and then one leading down towards this benzene having 2 chlorines. Next we have a terconazole. Terconazole would be a tertiary 3 degree. So this carbon 1, 2, 3. So remember there are 3 carbons here, CH3, CH3, CH attached to a 6-membered ring with 2 nitrogens, then a benzene ring, and oxygen which is attached to a CH2 group, which will be attached to a 5-membered ring of containing 2 oxygens. So this carbon right here will be attached to one would be attached to a benzene ring with 2 chlorines, and the other one to a triazole, so a triazole ring with a CH2 in the middle. This is a terconazole. Next we have the MOA of azoles. So how will azoles work? So azoles inhibit fungal cytochrome P450 enzyme, that is 2-demethylase, which is responsible for converting lanosterol to ergosterol. So as we have seen the name AZOLE, so LE is there, so it will inhibit the fungal cytochrome P450 enzyme of 2-demethylase, so it won't allow the conversion from lanosterol to ergosterol, that is the main sterol in the fungal cell membrane. Now, the second thing it will do is inhibition of mitochondrial cytochrome oxidase. So, since this mitochondrial cytochrome oxidase is inhibited, it will lead to the accumulation of peroxide that causes autodigestion of the fungus. Next is imidazoles may also alter RNA and DNA metabolism. So, what are the 3 things that azole does? Azole will inhibit the conversion of lanosterol to ergosterol by using the enzyme 2-methylase, then inhibition of mitochondrial cytochrome oxidase leading to the accumulation of peroxide that causes autodigestion of the fungus, and then imidazoles may also alter RNA and DNA metabolism. Next we have alkylamines. So in alkylamines the example was terbinafine. Now there were 3 things over there. There was a lanosterol, there was a ergosterol, and before these two there was a squalene. So squalene to lanosterol conversion will be inhibited by alkylamines. Now one example is terbinafine. So in terbinafine what we will remember is there is a NAF. So NAF is naphthalene, NAPHTELENE. So naphthalene. So in terbinafine we have a naphthalene group attached to a CH2, which is the common for all of our antifungal agents. Then we have a nitrogen which is attached to a carbon chain. How many carbons? 1, 2, 3, 4, 5, 6, 7. Ter will consider it as 10. So we'll consider 10 carbons. How do we do that? We'll draw a naphthalene first. Then we will give it a CH2, then a nitrogen. We'll give 1 carbon here. Then we count to 7. 1, 2, 3, 4, 5, 6, 7. Now we will count the carbons from the right hand side to the left hand side. So 1, 2, 3. So after the third carbon we will give it a triple bond. We count again 1, 2. After the 2 carbons we will give it a double bond, and then 1. So we need a single bond right here. So we will count now 1, 2, 3, 4, 5, 6, 7 carbons, plus 1 8, plus 1 9, and then 9. So 10 is it? We will remember. Next we have the MOA of alkylamines. Now alkylamines are also known as squalene epoxide inhibitors. Now squalene epoxide inhibitors, what they will do is they will inhibit fungal squalene epoxidase, so it will decrease the synthesis of ergosterol. Since we saw azole was L2E, so before lanosterol we also have a squalene. So this will inhibit the conversion of squalene to lanosterol by inhibiting the enzyme squalene epoxidase. So it decreases the synthesis of ergosterol. If there is no lanosterol, there is no ergosterol. Then it will cause the accumulation of squalene, which is also toxic for the organism and causes the death of the fungal cell. Next we have flu cytosine. So first we will see what is the structure of cytosine. So cytosine is written like this. It's a benzene ring with two nitrogens, a double bond here and an NH2 here. Now since it is a flu cytosine, we will give it a fluorine group right here and then the double bonds. So this is a flu cytosine. It is derived from cytosine, which will be drawn as a benzene ring along with two nitrogens, a double bond O, a NH2 group attached right here. This is a cytosine. Flu cytosine is just the addition of another fluorine group. So it is converted within the fungal cell to 5-fluorouracil. It is not in human cells, only in the fungal cells, and it will inhibit thymidylate synthetase, which inhibits DNA synthesis. So it interferes with the DNA synthesis. Next we have amphotericin B. So amphotericin B is obtained from Streptomycin nodosus. What is the mechanism of action? It will disrupt the fungal cell membrane by binding to ergosterol. So it alters the permeability of the cell membrane, leading to the leakage of intracellular ions and macromolecules. Now if all the vital micromolecules and intracellular ions come out of the cell, there would be some disruption in the cell content, and this would lead to the death of the fungal cell. Now what will happen is, in short, amphotericin B will bind to aldosterol in the fungi cell. There would be a pore formation. It will leak out the molecules and then there would be cell death. Now let us look at the structure of amphotericin B. Now it might look a little difficult. Trust me, it is very easy. Let us see how to draw an amphotericin B. For the structure, we will draw 8 mountains first. 1, 2, 3, 4, 5, 6, 7, 8. Now from this mountain we start here. The tip will have an oxygen. The next valley will have a double bond O. Next valley an OH. The third valley another OH. We skip the next valley, we go to the tip, we give it an OH. The next valley again an OH. Next valley again an OH. And then what we do in the next valley is, here we will give an oxygen down and an OH on the top. And using this we will form a benzene ring. In this benzene ring, right here we will give an OH. Here we will give a COOH. From here we will take it down, make a mountain, but like a flipped mountain. Then we will give a 7 mountains here. 1, 2, 3, 4, 5, 6, 7. Now from here we will take an oxygen and we will give it a benzene ring. In this benzene ring we will give an oxygen on the tip. Right here we will have a CH2, then an OH, an NH2 group and another OH. So we have alternating O's as well. O, CH2, OH, NH2, OH. Now here in these 7 mountains we will give double bonds. So count again. 1, 2, 3, 4, 5, 6, 7 mountains. Now right here we will complete this ring. We will make it kind of as a benzene ring. This one too. Then here we will give a CH3. Here also CH3. In the middle we will get an OH, and here as well we will give a CH3, and this will give you your amphotericin B structure. Let's count and check whether we are correct. 1, 2, 3, 4, 5, 6, 7, 8. So the 8 mountains, tip oxygen, down double bond O, OH, OH. We leave the next valley, we go to the tip, give it an OH, then down two OHs again. In the next family, on top we will give an OH, down an oxygen. The next bond here will be an OH group. Then coming out of this would be a COOH group. This O attached right here. Go down, make this a valley, give it an oxygen, a benzene ring attached with an oxygen, CH2OH and H2OH, and it's done. Next we have 7 bonds. 1, 2, 3, 4, 5, 6, 7. So we have the 7 double bonds. Followed by this we have the CH3 group, OH group, and a CH3 group attached over here. Next we have Nystatin. Now Nystatin we have same thing, 8 mountains first, 1, 2, 3, 4, 5, 6, 7, 8 mountains right here. We'll complete this. Okay, and we get 7 mountains right here, 1, 2, 3, 4, 5, 6, and the 7 mountain right here. And we give 4 double bonds this way, 1, 2, 3, 4, a gap, and 1, 2. We complete this one right here. Okay. Next what we do here is we give an oxygen on the tip, a double bond down here, OH, OH. Now here we will give another OH. We'll take a gap right here and we will give it to the tip on the top. Then another OH. Then again here we will get an OH up, an oxygen here, attach it right here. Then we will give an OH here, a COOH here. Attached to this will be an oxygen. With the oxygen we will give a 6-membered ring with oxygen at the tip, a CH3 here, CH3 here, a OH right here, and H2 here, OH here. Now after this right here we will give a CH3, a CH3 here, a OH here, a CH3 here. So Nystatin, it is also a polyene macrolide and it has the same mechanism of action as that of Amphotericin B. The uses would be oral candidiasis, conjunctivitis, and cutaneous candidiasis. Now, what is the difference between Amphotericin B and Nystatin? Now, these are the differences. Now, in Amphotericin B, there are only 2 OHs here after the double bond O, and the third one would be right here. So, here there are 3 OH groups, and this OH is shifted to the next mountain right here. So this is the difference. This will be continuous, this also will be continuous. So instead of this mountain right here, this OH is given over here, and then this OH would be shifted from here to here. Next we have this double bonds. So this has 7 continuous double bonds. In here we have 2 plus 4. So there is a gap in the middle, and then 2 double bonds, 4 double bonds. So this is the difference between an Amphotericin B and Nystatin. To see the similarities, they are both 38 membered microcycles. They are both belonging to the family of polyenes. So next we have Griseofulvin. Griseofulvin is obtained from Penicillium griseofulvum. The mechanism of action of Griseofulvin is Griseofulvin will inhibits the mitosis, which will interfere with the microtubule function. So what will happen is, because of interfering with the microtubule function, there will be disruption of the spindle fibers. Now since there is a disruption in the spindle fibers, there will be no formation of cell, and this will lead to cell death. So no formation of cell because there is inhibition in replication. So since there is no replication, there would be cell death. The uses are candidiasis and dermatophytosis. Now how do we remember the structure of Griseofulvin? Remember, Griseofulvin belongs to the class of benzofuran. That is heterocyclic benzofuran. So what do? We draw a 6-membered benzene. Attached to it would be a furan ring. Okay, so 1, 2, 3, 4, 5 carbon. and attached to this would be another benzene ring. So since this is a benzene ring, we will give this benzene ring OCH3, alternatively another OCH3. Now a chlorine right here. So we will think like chlorine will break down OCH3 into O and CH3. So OCH3, there's a chlorine in the middle, next ring has an oxygen. So the oxygen is done, like OCH3 will be broken down into O and CH3. So oxygen is done, next remaining is CH3. So right here we will give a CH3. Now in the furan ring, this is also a double bond. In the furan ring, what we will imagine is this one. After OCH3 furan ring, we will get a double bond O. So since double bond O, we will think like double bond O will make a copy. So OCH3 double bond O. So the next will also have OCH3, and then this double bond O will come at the alternate position. Double bond O. To make up the valency, a double bond right here. So this will be the structure of Griseofulvin. Next we have Caspofungin. So since the structure of Caspofungin is very difficult, we'll only learn about the mechanism of action. So it will inhibit the synthesis of fungal cell wall by inhibiting the synthesis of beta 1,3-D-glucan, leading to the lysis and the cell death. If you remember, in the structure of a fungus we had seen that there is a cell membrane, there is a cell wall, and in the cell wall there are certain beta structures, that is glucan structures. One of them was beta 1,3-D-glucan. If you all want to check, please go to the first page and check it again. We had beta 1,3-D-glucan which made up the cell wall. So what will happen is it will inhibit the synthesis of fungal cell wall by inhibiting the synthesis of beta 1,3-D-glucan, leading to lysis and cell death. Next we have other topical agents. In other topical agents we have undecylenic acid, and then we have Tolnaftate. Now undecylenic acid, deca, un deca. So un means 1, deca means 10. Now if you add 10 and 1 you will get 11. So it's a 11 carbon containing chain with a ending group of double bond OH. So let's count how many carbons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So in the 11th carbon we will have a double bond OH, and in the first and second we will have a double bond over here. So we'll draw 11, 1, 2, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So in this one we'll give a double bond O and OH, and between this first and second we will give a double bond. Next we have Tolnaftate. Tolnaftate, will break it down. Tolnaftate. So tol means toluene, neph is naphthalene, T is for the thio group, and 8 is for the COOH group. Now how do we put it together? We'll draw the toluene group first. So we will draw toluene this way. So a benzene ring with a CH3. This is a toluene. Next we will draw a naphthalene group. So one benzene, attached to it would be another benzene. Now how do we draw a 8, that is carboxylic acid? C double bond O and OH. Now since it is a naphtate, T is the thio group. So what do we do here is we add a C, instead of double bond O we will add a S, and then a O group attached here and an H. So we will draw this way. Since Tolnaftate, naphtate, so close to the naphthalene we will draw. So we will add O, C double bond S, and then here what we will do is we will attach this to a N and CH3 group, and this N will be attached to this group right here. Now this is the extra one we need to draw over here in Tolnaftate. Next we have the synthesis of Tolnaftate. Now how do we synthesize tolnaftate? For this, first what we will do is we will draw a basic structure of tolnaftate in the corner. So a naphthalene group, attached to it is a 8 group, so O C double bond S. Attached to it would be an N CH3, then a toluene group attached to it. Sorry. So this is our reference structure. So what do we see first here? We see this group right here. So this can be called as, since there is an oxygen right here, we will call it nephthol. So OH, so 2-nephthol, or we will also call it beta-nephthol. So 2-nephthol we will take, and we will add thiophosgene. Now if we add thiophosgene, which is C attached double bond S and Cl, thiophosgene, what we will do is this H will go and attach to this Cl. So this will give us HCl, which will be removed, and this oxygen will attach to C double bond S and Cl. So we get this structure right here. So we need only till this one. Now we have a chlorine which can be removed by using a nitrogen. So will be removed by a hydrogen. So what do we do? Whatever you need, the remaining structure, we write it down here like so. So a benzene ring with a CH3 group attached with an N and a CH3, and then we need a H to be to remove this chlorine group. So a H right here. So this H and this Cl will give us HCl. So there will be removal of another HCl group, and then we will get tolnaftate. Next we have the synthesis of miconazole. Now to remember miconazole was, we'll draw the structure here, this, a chlorine here, a chlorine here, attached to this was a CH2 group, then an oxygen, another CH2 group, another benzene here with 2 chlorines, attached to this CH2 was another CH2 with a imidazole ring. So what do? We will take this part first, imidazole ring, okay, and we will start with a 1-bromo-2,4-dichlorophenyl acetophenone. So we will have these 2 chlorines attached to it, a carbon attached to it, and an oxygen attached to it. So this part, so CH2 attached to it. So we have we will take a 1-bromo-2,4-dichlorophenyl acetophenone. So we will add an imidazole ring to it. So what will happen is this, since it's a Br right here and there is a H attached here, this will be removed as HBr, and we will get this chlorine group attached with C double bond O CH2, and then this imidazole ring attached right here. Now when we put NaBH4, be reduction reaction. So reduction reaction, as in this reduction means removal of oxygen and addition of hydrogen. We have a OH group instead of double bond O here. Now instead of this H group attached to O, we need this group right here. So we will add this group, but the only difference would be we will add a Br attached to this CH2 group. So a chlorine attached to CH2, and instead of anything else, we will have a Br group. So this H and this Br will be removed right here, and we will get the structure of miconazole. That's all we had for today. Thanks for listening. I hope you had learned. I hope you have learned a lot from this chapter. Antifungals is a very important chapter. So if you need to see the video once again to understand properly, I highly recommend you watch it again. This chapter is very important with the exam perspective, and also it's a very interesting structure. If you have any additional questions regarding this chapter, please comment in the comment box. I will get to you soon. So that's all we had for today. Thank you. Mogaso.